we have Dr. Markus Paul Muller from the Institute for Quantum Optics and Quantum Information, Vienna, Austria. Let me give a brief introduction about him first. Markus Müller is a theoretical physicist and research group leader at the Austrian Academy of Science Institute for Quantum Optics and Quantum Information in Vienna. After studies of physics and mathematics, he obtained his PhD in 2007 in Berlin and moved on to a postdoctoral position at the Perimeter Institute for Theoretical Physics in Canada. Before moving to Vienna in 2017, he has been a junior group leader at Heidelberg University and an assistant professor and holder of a Canada Research Chair in the Foundations of Physics at the University of Western Ontario. Interestingly, Mueller dislikes speaking about himself in the third person and prefers first person approaches. Over to you, Professor Mueller. So, without any further delay, let's start the talk. Thank you.
Okay, great. Thank you very much for the great introduction, and thank you to Varun and Vasudeva for inviting me to give a talk here. It's a great opportunity, and I would like to thank you for this. Okay, so my talk will be about a first-person approach to quantum paradoxes and beyond. It's actually a collection of two things which overlap a lot, as you will see during the talk. The first part is a part on reconstructions of quantum theory. So I begin with, in part one, to talk about probabilistic theories beyond quantum theory. These are theories that generalize classical and quantum probability theory, and they allow us to have a framework in which we can derive the abstract formulas of quantum theory from simple principles. This is called a reconstruction of quantum theory, and I will show an example of that in the second part of the talk. I will argue that this indicates a certain view on the quantum state that also Professor Leggett has just sketched, which is that essentially quantum states are catalogs of probabilities, probabilities of what some observer will see in the future. And this brings me to the second part of the talk, which has to do with Wigner's friend and assigning probabilities of future observations in more complicated scenarios. I will talk about recent work with Caroline Jones, my student here in Vienna, about first reproducing some of the phenomena of Wigner's friend essentially classically, and a conclusion that we draw from this, namely that there is a phenomenon that we call restriction A that underlies not only Wigner's friend, but several other puzzles in the foundations in philosophy of physics. It's essentially the view that physics sometimes fails to allow agents to predict their own future experiences. I will sketch in the last part a kind of personal view of what that might tell us about quantum theory in the world if I get there. So I might have to skip a few parts because it's a bit ambitious, but we will see where we go. So let me begin with probabilistic theories beyond quantum theory and reconstructions of quantum theory. What is the motivation for this kind of work that many other colleagues and I have been pursuing for a couple of years? One motivation goes, for example, is expressed by John Wheeler here, what he said in the year 2000, according to the New York Times. John Wheeler said that quantum physics has explained the structure of atoms and molecules, the behavior of semiconductors, the comings and goings of particles from neutrinos to quarks. Successful, yes, but mysterious too. Why does the quantum exist? So why do we have this sort of very abstract, mysterious, counterintuitive theory and not some other theory, perhaps, that seems to describe everything we see around us? Yeah. And this is the motivation for certain work, and also our result that I'm showing here, and related results by other colleagues, including Giulio Chirivella and Czeslaw Bruckner and other people, where we derive quantum theory from simple principles. These principles are arguably very natural, and they are operational information theoretic. So they have to do with probabilities, with what we can do in a laboratory, with operations that we can perform. So in a way, you could answer why the quantum, in a way because nature obeys these natural principles, if you want. The role model for this is a historical one. So when you think of the Lorentz transformations, like here in this picture, that they have been written down in the 19th century. But then why do we have exactly these equations and not others? And that's what Einstein answered. So he derived these transformations from two principles, essentially, from the light principle, that the speed of light is constant, and from the relativity principle. And the goal of this sort of work here is to do the same for the abstract formalism of quantum theory. Rather than writing down the postulates with Hilbert spaces and operators and so on, we want simple principles that prove us that these equations and mathematical structures must be the case. Okay, now how do we do this? Well, one underlying view of, say, Einstein's derivation is that relativity is, in some sense, one of many possible theories of geometry of space and time. So we could say the usual view of Euclidean geometry of Galilean space-time is a special case, a very simple one. Relativity in Minkowski space is another one. There would be many others. And in this framework, we can derive the Lorentz transformations with these two principles that I've mentioned. Our derivation of quantum theory from principles views quantum theory as one of many theories of probability. So these are theories that describe the probabilities of observations and of the correlations between outcomes and so on. The most intuitive instance of this would be classical, quote-unquote, classical probability theory, where you just have probabilities of events in the usual sense, a non-classical quantum sense. But first, to see how that fits together, we need some intuition about how probabilities in physics could actually be more general than quantum and classical. And one example how this could be the case is given by Bell scenario. So in a Bell scenario, you ask, well, what if I have two space-like separated laboratories? And I think of agents Alice and Bob in the local laboratories. Alice chooses some input, perhaps a setting of her apparatus X. Bob chooses Y. They do a measurement locally, a physical process gives them an outcome A for Alice and B for Bob. And if they're space-like separated, we assume that they can freely choose their input. There may be some information from the past, some shared randomness affecting what they see, is lambda. Then we know in classical physics what this can be. So in classical physics, classical probability theory gives us this equation here on the slide. We have a distribution over these lambdas, and depending on lambda and the settings, you get your outcomes. In quantum physics, we have a general equation. You have products of measurement operators acting on some potentially entangled quantum state. And certainly, but in both cases, you have the no signaling conditions satisfied. And this is also physically very intuitive and important. For example, if you just look at Alice's outcome A, then the probability of A, given her setting X and Bob's setting Y, turns out to be independent of Y. This means no matter what Bob does to his lab, Alice in her lab will not see a statistical difference. That's important because otherwise they could use it to send information instantaneously, even if they are very far away, faster than light, so to speak. And the same holds the other way around, from no signaling from Alice to Bob. Now, quantum theory shares this property with classical probability theory, but it admits more general probabilities in these experiments, which can be demonstrated by the violation of Bell inequalities. One particular Bell inequality would be the CH-SH inequality, where you compute these correlators CXY, which is look at the expectation value of the outcomes, their product, whether they're correlated or anti-correlated, depending on the settings. And then this expression here is always lower upper bounded by 2, as we also seen in the previous talk, classically. Whereas in quantum theory, you can violate this, and instead of 2, rather than 2, you can get up to 2 square root of 2, which is known as the Cyril zone bound. So in this sense, quantum theory allows more general probability tables than classical theory. Now in 1994, Sandro Popescu and Daniel Rohrlich asked, is this everything we could have? So are the quantum correlations actually the most general probability tables that satisfy this non-signaling principle, or could there be more? And the perhaps surprising answer is there could be more. So the answer is no, it's not the most general way that quantum theory behaves. And an example is given by what's called now the Popescu-Rohrlich box correlations, PR box correlations, which are here in the table. The idea is that with the settings X and Y, if they happen to be +1 and +1 for Alice and Bob, right, then the outcomes are anti-correlated. So they either get +1, -1 as outcomes or -1, +1. But for all other 3 setting pairs, they get perfectly correlated outcomes. Now, if you compute this expression here, the CH-SH value, you get a value of 4, which is more than quantum theory's 2 square root of 2. So what this tells you is that this probability table here cannot be realized in a Bell experiment in quantum theory. It's also non-signaling. Even if you had it, you could not use it to instantaneously signal, right? So, but it shows you that in principle, there are more general correlations possible in quantum theory predicts. You can draw pictures like this that people sometimes do, that the sets of correlations are convex sets. The classical set C is a subset of the set Q of quantum correlations, which is a subset of the no signaling correlations. And it turns out that you can see these correlations, the classical ones to come from classical probability theory, Q from strong quantum theory, and the others come from some other theories, for example, toy theory called box world that some people have come up with. So these are three examples of what's called a generalized probabilistic theory. And to understand what a generalized probabilistic theory is in general, you would think of a typical laboratory situation where you have perhaps a preparation procedure. You press a button, you prepare a state, maybe some photon or so. You have a transformation, so something you can do to the system. And in the end, you will do a measurement that gives you an outcome that you can read off. You can think of classical coin tosses in this picture. So whenever you push the button, then some of the preparation device performs a biased coin toss, perhaps. Yeah, what does the transformation do? Well, maybe it takes the coin and inverts it, puts heads to tails and tails to heads. And maybe the measurement, what it does is it looks whether it's heads or tails, and it flashes a light, a red light, if it's heads or so. In this case, you would say, well, what the preparation device does, it prepares a state omega. Omega is not just a probability distribution. Yeah, the statistical properties of what comes out of the device is described by two probabilities, P of heads and P of tails. What is a state space? State space is like the set of all possible states. So for a classical bit or a classical coin, it would look like this. Yeah, you could have a fair coin, which is in the middle, or completely biased coins, which are deterministic and the other ends, and like all the probabilistic mixtures between them. Okay. And what does a transformation do? For example, you could move heads to tails and tails to heads, which would be this map T here. You see this is a linear map and that it maps states to states, as it should. And then every measurement outcome has a probability. For example, if you're interested in the probability that you have heads, given that your state preparation was omega, well, all you have to do is read out one of the components of the vector, and this is linear. So it's an inner product with some other vector. And a quantum bit is pretty similar formally and operationally. What the preparation device now outputs is, you would say, a qubit state, for example, of a spin 1/2 particle if you want. So it could be a pure state, then it's a superposition of 0 and 1. Or in general, it could be a mixed state, a 2x2 density matrix. And it's well known that all these states can be visualized in this form. So the state space of a qubit is just visualized and described by a Bloch ball, which is a three-dimensional ball, right? And this is well known. So you can write states with like two angles, essentially, and the pure states then give you the sphere, and the mixed states are in the center. So this is a qubit state space. Unitary transformations could basically rotate this qubit Bloch ball, right? And measurements means that you take the Born rule. So measurements are described by, for example, projection operators or positive operator valued measures in general, and they give you probabilities between 0 and 1. So for a general probabilistic theory, you ask, what is a state here? Well, it's the thing that allows us to determine, for all possible measurements, the probabilities of all possible outcomes. For example, in quantum theory, it's a density matrix. If I want to know what probability of a spin up I find when I decide to measure the spin, whether the spin is up or down, then I can just use rho and plus the Born rule to get the probability. What's the state space? It's the collection of all states that a system could be in, closed under statistical mixing, right? So statistical mixing means maybe you toss a coin or some dice, and then if the outcome is even, you prepare some state omega, and if it's odd, you prepare some state tau. And the total procedure should also be a valid preparation procedure. And then you get a state that's like the 50-50 mixture of these two states, and you want that always to be possible. And so this means that your state space should be convex. So if you mix together states, it should still be a valid state. Now, quantum theory, the states would be the density matrices, the Hermitian matrices over the complex numbers that have trace 1 and are positive semi-definite. In classical probability theory, this is just vectors of probabilities that sum to 1. What's transformation? Transformation maps some ingoing state to an outgoing state. It must be linear because it must play together with mixing in a nice way. And you would say it's reversible if you can undo it. So if there's an inverse, and that's also transformation. In quantum theory, transformations would be the completely positive, trace non-increasing maps, and the reversible ones are the unitary maps. How do you describe measurements? Well, suppose you have an n outcome measurement, then you would say would need n linear functionals that you can pair with your state to get a number, which is the outcome probability. Right? So for quantum theory, you would just have these measurement operators ei, and you pair them with a state omega by taking the trace. And yeah, then you can have all kinds of theories and systems of probabilistic theories. You can have a classical bit that I've shown you and the quantum bit. A classical trig, three-level system, would look like a triangle. A quantum trig looks very interesting. It's a very complicated beast, the set of 3x3 density matrices. It's 8-dimensional and very curved and whatnot. But you could have anything. So something that people in the field of some study is called G-bit, which is just a square state space. But you can have anything. So anything that falls into this idea that you can have states, preparations, and measurements and mixing. So this means there's a large landscape of such theories. We have like classical probability theory, quantum theory in the middle, many other theories, something called box world, operator algebraic theories, and others. They look all very different. Now, the goal of this research is to find a small set of simple physical or information theoretic principles that would really single out quantum theory from this landscape of theories. And the role model of this, again, is Einstein's relativity principle and light postulate. I would say that the landscape of theories is the geometric theories. And what's singled out there is Minkowski space-time among many, many others like hyperbolic and whatnot spaces. Okay, now can we use this idea to derive quantum theory from simple principles? There's a long history of reconstructions. It goes back to Birkhoff von Neumann in the 30s. There's a lot of work on quantum logic, which had a very similar goal. Now, with the advent of quantum information in the 90s, things got a bit better because technically people realized that it's good to look at finite dimensional systems is good enough. And this made things technically much, much easier. And in 2001, Lucien Hardy published a groundbreaking paper, Quantum Theory from 5 Reasonable Axioms, where he sort of did this, achieved this goal up to a problem. I said, no, I cannot really. So I get an infinite sequence of theories and I pick the simplest one, and that's quantum theory, right? But then later on, a couple of people finished his work, completed this work. So there's among some of the people here on the slide and also us. So how do we do this? Let me give you a kind of example derivation of quantum theory that's in this paper here with Luis Massanes, Remigijus Augusiak, and David Perez Garcia. So we have 4 postulates. And the first postulate is called continuous reversibility. It means that reversible transformations can, in principle, map every pure state continuously to every other. So if you think of a spin-1/2 state where the spin points in some direction, then you can time evolve it slowly to get to point to any other direction that you want. So this is true in quantum theory because every pure state is connected by the other pure state by some unitary. Here we regard it as a postulate. The second postulate is called tomographic locality, and it says that the state of some composite system should be completely characterized by the correlations of measurements on the individual components. So think of a state here, psi, doesn't have to be a quantum state, but it's shared between 2 laboratories, say Alice and Bob. And Alice and Bob would like to find out what the state is by doing tomography. So maybe they have many copies of that state. But they can measure only locally. Alice measures in her lab, Bob measures in her lab, and then they talk on the telephone what they found. Turns out that this is sufficient to reconstruct the quantum state. They don't have to meet in the middle and make one big entangled measurement necessarily. And that's called tomographic locality, and you can use it as a principle for any kind of probabilistic theory. It's also true classically. The third postulate is called existence of an information unit. And the idea is somehow that it can encode everything into bits, sort of. So the claim is that there is some system, the U-bit or universal bit, such that every other system can be encoded into a sufficiently large number of such U-bits. And also if you have 2 of these U-bits, then they should be able to interact. There should be some reversible time evolution on them that makes them correlated. So that's true classically. You can probability distribution over, say, a trig. You can encode it into a probability distribution over 2 bits and go back. encode and decode. Quantum theory is also true. You can encode every finite dimensional quantum state into a sufficient number of qubits. And here it is taken as a postulate. The fourth postulate goes back to a proposal by Zeilinger a long time ago, Anton Zeilinger. And it says that the U bit should actually deserve the name bit. So it says that if a universal bit is used to perfectly encode one classical bit, then it cannot simultaneously encode any further information. Use a bit, use it up, and then you've used it up. You can do nothing more to a universal bit, essentially. Now you can show, with lots of mathematics and group representation theory and so on, that this gives you quantum theory. So if these four postulates hold, then you cannot have any probabilistic theory, but it must be exactly this here. The state space must be the 2 to the n by 2 to the n density matrices over the complex numbers, and the reversible transformations must be exactly the group of unitaries that acts by rho goes to u rho u dagger. And this is quite remarkable because if you remember, we have put no assumptions in on anything like complex numbers, operators, or even algebras that you can multiply anything. So this comes out from the proof. It's not something you put in. Also, it's interesting to see that if you drop the word continuous in postulate 1, so you just have reversibility rather than continuous reversibility, then you obtain classical probability theory. We have discrete bits where you can discretely map every pure state to every other, but not continuously in time. Good. So for example, here you can understand a bit graphically why a quantum bit is described by a Euclidean ball. Remember the 3D Bloch ball that we've seen? Why is that the case? To understand that, you need only two of these postulates, postulate 1 and 4. And when you think of continuous reversibility, it means that every pure state that sits on the boundary of a state space can be continuously transformed reversibly to every other. This means that there must be a group acting on your state space, which maps everything on the boundary to the other points on the boundary. So everything must be essentially rotations, and then the pure states must lie on a unit sphere according to some parametrization. We don't know the dimension of the unit sphere, but it is a unit sphere. Maybe some parts of the unit sphere are missing. What if there are some parts? So if nothing is missing, if it's a total sphere, then you can encode one classical bit, say by either preparing a state on one side or the antipodal state, like for a qubit. But if it's not the full ball, and if there are some points on the sphere missing, then you could encode one bit and a little bit more by just not only deciding to encode whether you want like omega 0, omega 1, but you can also decide whether you encode omega 1 or omega 1 prime, which is both somehow on the other side. You can make that mathematically rigorous, but that's a bit the idea. So you do get a Euclidean ball. But why is this ball now three-dimensional in quantum theory as for the qubit Bloch ball, which describes the 2 by 2 density matrices? So the idea is now that when you look at two of these bits, and you say there must be some composite state space that describes two of them, and we don't really know anything about that, right? All we know is for every single bit, we can do all the rotations essentially. We can count parameters and say what the dimension is of the state space AB, and that's the equation here. Why can we do that? Because we know that local measurements and correlations determine the state. This gives you the definition of the dimension. And then you can do like very hard work and come to the following theorem, like a bit of group theory and representation theory and convex geometry. You say, among all the possible dimensions of what the Bloch ball could have, and all the possible groups that could act on one of the Bloch balls, there are only two possibilities. The first possibility is somehow a trivial combination of state spaces, where the group of transformations of AB, anything you can do to both the bits, is just the product group. So it means your bits can never talk to each other. You can only evolve them separately. There's another, like only one single exception, which is in dimension 3, only for three-dimensional Bloch balls. And if you allow all rotations for a single Bloch ball, you get one solution, which is interesting, and it turns out to be the quantum solution. So the group for the two bits is then the unitaries over a four-dimensional Hilbert space, and you do exactly two qubit quantum state space. So these kind of strange generalized bits can only reversibly interact continuously in dimension, in like abstract qubit Bloch ball dimension 3. proof idea, let me skip this, but all you demand essentially is that the probabilities must be between 0 and 1. That's everything you need to assume. Now, what does this now tell us, right? So this is perhaps the interesting question beyond the techniques. So for me, it says that we should understand quantum theory as a theory of probability. So that's a bit like what Professor Leggett said in his last lecture, and referring to Ballantyne, for example. It's the idea that quantum states essentially represent something like belief or knowledge or information, just probabilities. Why? Well, we've seen that the complete Hilbert space formalism, including the use of complex numbers, of operators, and the state update rules, this I haven't shown you, but that also follows from a few simple information theoretic or probabilistic principles. So in this picture, for example, you don't need to talk about collapse really as a kind of fundamental physical process happening, which is say this is only Bayesian updating. When you learn new information, your probabilities update. What is time evolution in this picture? It's just correlation with some idealized clock variable, right? What's the superposition principle? The superposition principle is not a principle, it's more a mathematical accident. It comes from the fact that the pure states can be written as psi, and then you can take the square root, and then you get a superposition principle. Now, I think this is very suggestive, and it supports the idea that quantum states should be understood as similar objects as probability distributions. Now, what about certainly Everettians would disagree, for example. You think for many worlds, like interpretation, it would be very different. But now my challenge would be to Everettians, for example, to do something similar. So can you perhaps start with a landscape of, say, theories of many worlds, write down a few simple principles, and from this prove that quantum theory is the unique many worlds-like theory that satisfies these principles. So far I haven't seen this. It would be exciting to have that, but given the absence of this in all other interpretations, so far I see these reconstructions as evidence that we better view the quantum state as something like a piece of information or belief or knowledge, expressing just probabilities of future observations. All right, now this was sort of the first part of my talk. Now let's see how far I get with the second, which has to do now with more than one observer, with Wigner's friend, and with some more conceptual takeaways and views and insights that we think we have here. The idea, what I did with Caroline Jones here, is to look at the Wigner's friend scenario and to see which parts of it are like genuinely quantum or whether some parts of it are more generic. The answer is there are more generic parts of it that have to do more with what it means to be an observer and how observers can actually agree or not. Anyway, so let's go there. There are different versions of this Wigner's friend thought experiment. The simplest one, going directly back to Wigner, is really just you have a friend in a laboratory, say in this box here, and a system, say R here in a quantum state. The friend measures the system and sees an outcome. For example, the friend sees spin up. Whereas Wigner, who's outside of the laboratory, would, if the laboratory is perfectly sealed, for example, describe the evolution of the box as a unitary time evolution and say this is just in an entangled state now. Right? So Wigner's description would be to say that after the interaction, in the laboratory you have a superposition state, like this one. Whereas Friend's description would arguably be either 0, 0, so she has seen 0 and the system is in state 0, or 1, 1. So you have a diverging description of what's going on in the laboratory. Now, you may say, well, this is not so surprising. Different agents have different amounts of information about the same physical situation. That's why they may assign different states. But then there have been this recent extended or multi-agent Wigner's friend scenarios, which combine these ideas with ideas from Bell's theorem to derive really no-go theorems. No-go theorems about the kind of joint existence of all the observations of all agents under some assumptions. Now, as I argued above, like the quantum state should be seen as a kind of catalog of probabilities. What probabilities of what? Well, of sort of future observations or outcomes or experiences that some agent has. This agent may not necessarily be human or conscious. but it's a sort of referent for whoever assigns these probabilities for future observations. Now, it's perhaps not surprising that if you begin with this, then these probability assignments will not typically fit together into a joint description, like a joint probability distribution. The idea here is that then what we call the world may in some sense just be a mosaic, so to speak, of the more fundamental first-person perspectives, where each agent has its own probability for future observations. Good. So let's see how we can derive some aspects of Wigner's friend classically in some fun science fiction-like scenarios. Here is the Fauchiger-Renner scenario. I have to brush over it quickly, so I would invite everybody who hasn't seen this to look up the details because I don't have time for it. But the idea is that you have basically two friends in two boxes. One of the friends sends a physical system to the other friend. Two Wigners measure the friends and their laboratories, and then suddenly you find some statistics that violates the conjunction of three innocent-looking assumptions. These assumptions are that quantum theory is universally valid, that measurement outcomes must be single-valued, and that the predictions of different agents are consistent. The most interesting aspect of this is the third assumption, C, consistency. What does it mean? It means this here. So it means, suppose there's agent A, like on the right here. A prime. And A prime knows that the outcome must have been Z equal to +1/2, according to the theory she's using. Also, agent A knows that agent A prime knows that this is the case. But if that's true, then agent A should be able to conclude, I know that Z equals +1/2. So if an agent knows that another agent knows that something is the case, then the initial agent itself should believe that this is the case. This is what's called the consistency assumption here. Famously, Fauchiger and Renner have shown that this is untenable if you also demand the other two assumptions Q and S, quantum theory and measurement outcomes, single-valued. Now, we can have a similar, slightly different, but an interesting behavior in a classical thought experiment as well, which goes as follows. So we have two people, say Freyer and Wegener, I think that's how we call them, at the beginning of the experiment. But they live in a science fiction world. We have very advanced technology, so think of Star Trek. So what we can do is we can multiply them, like produce copies. So we copy them into n copies, each one in their own single laboratory. And then in the next stage, in each laboratory, a coin will be tossed. And if the coin shows heads, then Freyer will be again multiplicated. So there will be m copies of Freyer, which are m equal to 2 in this picture. But if the coin is tails, then nothing is going to happen. All right. Now, that's a thought experiment. And now what Freyer and Wigner are asked for at the beginning of the experiment is a bet. So they can buy a ticket from a bookie for about 66 cents, so 2/3 of a dollar or euro, that wagers on the coin toss having shown heads. So if their coin shows heads, they get $1, otherwise they get nothing. Right? Now, in a way, you may say intuitively now, and we'll get to a more careful analysis in the next slide, that Freyer somehow, for Freyer, so the heads outcome is sort of amplified. So in approximately law of large numbers, if n is large and so on, there should be 2/3 of the Freyers will see a heads outcome and 1/3 of the Freyers will see a tails outcome. So she should buy the ticket. But for Wigner, it's like 1/2 of the Wigners will see heads and tails, so he should not buy the ticket. Turns out you can make this intuition rigorous and say here are 3 assumptions that can all not be jointly satisfied. One of them is due to Adam Elgar, and it's called Elgar's principle of indifference. Formally, it says that similar centered worlds deserve equal credence. It essentially means that if you know you're one of a number of copies that only differ about where you are, perhaps in the world, then you should assign equal probability of being one or the other. There's also now a principle that you can call like consistency for Fauchiger and Renner, but it's a probabilistic version of that. So it goes as follows. Suppose that an agent A says, I'm pretty sure that the agent A prime, reasoning with the same theory as the one I'm using and having the exact same knowledge of the world as I, is pretty sure that something is the case at time t. And then the agent A can conclude that I am pretty sure that this is the case at time t. So your friend in the laboratory uses the same physical theory as you and is pretty sure that something will happen. You both share exactly the same knowledge of the laboratory, then you should agree. Okay. Third principle is called no update on irrelevant information. Somehow it says that if Freya knows that all her future copies will undergo the exact same procedure until the experiment is completed, then her predictions for her future observations are unchanged if she's told which copy she is. Right. Turns out that all these three principles together, or even replacing Elgar's principle by some milder versions, where you don't have to have uniform distribution, run into a contradiction. So you can prove the theorem that these three principles cannot hold jointly in this experiment. It's just not possible. Now, let me say some clarification. So we do not claim by doing this here that the Frauchiger-Renner-Wigner's friend in this scenario here are ontologically similar, that something similar is going on in the world. We're not saying that. All we're saying is that there's a structural similarity between the two. And the structural insight here is it has to do with joint probability distribution. So everybody who knows about Bell's theorem knows that non-locality can be attributed to some sense into the non-existence of a joint probability distributions over all outcomes for all possible settings. Here, it turns out something similar is the case. So it turns out that there is no joint probability distribution of the observations of Freya and Wigner if this kind of uniformity, this Elgar's principle holds, is assumed to hold. So in some sense, when you believe Elgar's principle, then this rules out the standard use of Kolmogorovian probability theory with a single distribution. And this implies that you have very strange phenomena like these two very innocent other principles going to fail. And so there's no probabilistic consistency anymore necessarily, and and perhaps some update on irrelevant information or so. Right. Now, if you're an Everettian, a mini-worlder, then you might see an actually ontological similarity between this thought experiment and Wigner's friend. But you can also turn it around. You can say, well, since this kind of duplication that we've talked about messes up the structure of Kolmogorovian probability space, you can see this as a sort of explanation why the Everettians can tell the story and can try to give a sort of realistic underpinning of quantum theory by going to a many worlds picture. Now you can ask, well, but isn't, quantum theory is very natural. That's why we talk with Wigner's friend, but this duplication business, this is really science fiction. We don't have that for 1,000 years, so why care about this? But I would argue this is wrong. It's actually the other way around. So these Wigner's friend scenarios, first of all, they're extremely invasive on the friend and extremely delicate. You want, in the end, a laboratory experiment. We control the friend in the laboratory unitarily. This is extremely invasive and extremely difficult. If you look at the resource requirements, then this kind of classical duplication stuff is much easier. It can be done in something like 5 orders of magnitude of smaller resources than the quantum Wigner's friend scenario. So it's very natural in some sense to consider it in the same kind of ballpark or intellectual frame as Wigner's friend. Now, okay, another thing that you should look at if you haven't seen it, I find it is very fascinating, is this strong no-go theorem on Wigner's friend paradox by Bong and many other people, including Howard Wiseman, where you have another multi-agent scenario with two friends and two Wigners in some sense. And then it turns out that if here in this scenario, you violate a certain statistical inequality, like in a Bell experiment, here it's called the local friendliness inequality, then the following three propositions cannot all be jointly true. This is locality, that you don't have signaling between space-like separated arms of the experiment. Well, we here no superdeterminism, so you have a free choice of settings, essentially, and absoluteness of observed events. Now, if you look at the fine print of what absoluteness of observed events means and how it is defined, then it says that for every pair of settings x and y chosen by these two Alices and Bobs outside of the boxes, there is a joint probability distribution over A, B, C, D, what Alice, Bob, Charlie, and Debbie see, which reproduces the observed distribution, which is that by Alice and Bob, as its marginal. Okay. So in the boxes, you have Charlie and Debbie. They see the outcomes C and D, but these outcomes are never recorded. They are not seen from the outside, usually, up to a few runs of the experiment when they open the box. But usually they are not seen. So all that's recorded are the outcomes A and B that happen outside of these boxes and their probabilities. Now you can ask, does this come from as a marginal distribution, from a valid distribution over A, B, C, and D? And the answer is, if you violate this inequality, the answer is no. You can also say, like, from the perspective of A and B outside the boxes, there simply is no random variable C that describes what Charlie sees. That would be stable over the course of the experiment. Why is that? Well, that's somehow because the quantum formalism doesn't give you that. The quantum formalism gives you the reduced density matrix, perhaps, but not the value of C as a classical random variable. Now, you can have a structural, you can say that this is ultimately the reason for the non-existence of the joint distribution over A, B, C, and D. But you can also conceptually say that in some sense it means that there is no unambiguous external notion of personal identity of Charlie over the experiments. Who or what is Charlie over the experiment, and how would I describe this as a random variable? Now we can simulate this behavior, aspects of it, not the violation of the inequality, and not the other absolutely fascinating aspects of this experiment, but just the thing I pointed out here, classically via duplication. And maybe let me not go through this, perhaps, but just look at, to save some time, at this kind of very simple thought experiment. Here you have Freya or friend in a box. Shortly after the experiment, she enters the box, and then the box's Freya is duplicated. So again, you have two copies. One of the Freyas will wake up in a blue room, the other one will wake up in a green room. And then you sort of reversibly merge the two Freyas back into one. So you do some sort of time reversal of the first step. And then Freya may exit the box and doesn't remember whether she's seen blue or green. Now, you can see here that you have a similar phenomenon here that motivated Adrian Kent to actually talk about the duplication loophole in the local friendliness paper. That here you also have a situation where it's unclear what it means to talk about the color that Freya sees. And it's not clear what kind of random variable that should be. However, you could certainly imagine putting yourself into Freya's shoes, do the experiment, and probably, maybe you would expect to see something and to forget it. So what you see here is a structural aspect that's similar to the local friendliness aspect, is that you would want to talk about a random variable that describes what the agent sees, experiences, but there is no such random variable, or it's at least unclear how to define it, and unclear how to put probabilities on the different possible values of it. Okay, now this kind of general structural phenomenon is something that we introduced a name now. We introduce a name for it called restriction A. A is for agent, a kind of restriction for agents, because we think that it underlies many other puzzles, directly or indirectly, in the foundations of physics and in some philosophical thought experiments. And to go there, so what do these probabilities mean that we talk about? So we interpret them as answers to the question of what the agent should believe to experience next. It's a bit like how we interpreted in the first part. It's how I motivated the probabilities that are implied by a quantum state. If you know you have a state assignment of a plus state and you do a 0-1 basis measurement, if that somehow you know this, then you should believe that the probability of seeing 0 is 50%. Similarly, you can ask, what should these agents in these exotic thought experiments believe, and what probabilities should they assign? And restriction A says now that physics doesn't always tell you that, essentially. So if our physical theories do not, and sometimes even cannot, give us the joint distributions for the future observations of n agents. This is sometimes even true for single agents if you have n equal to 1, like in the green and blue room example, but you can have it for more agents, then you are this incompatibility and extended Wigner-Friend scenarios. This is always relative to some theory T and some other background assumptions that you may have. Good. I maybe skip this, give some examples. So this kind of thought experiment by Bong et al. Is an instance of restriction A, because it tells you that under the assumptions they make, there is no joint probability distributions for Alice, Bob, Charlie, and Debbie, given the settings. Yeah. It just simply doesn't exist one. So for these n equal to 3 or n equal to 4 observers, there's no such distribution. What about this here? The fission and fusion, where I have two copies, they see both different colors. This is an instance of restriction A for n equal to 1. Our physical theories really do not tell Freya in this thought experiment what probability she should assign. Plausibly, she might decide to assign probability 1/2, but you could still have some claim, for example, that in 99% of cases, if she does it, she subjectively will see the green room. Yeah, and no experiment in the world that you can do as a physical experiment and publish a paper about will ever falsify it, because she forgets it afterwards. Right? So this is yet a different instance of what we call restriction A here. The standard Wigner's friend scenario is not, essentially because there exists a joint distribution. Use the Born rule separately for Wigner and Wendt and take the product state. Now, in this kind of classical thought experiment that we've shown, they also have an instance of this. So first of all, even for a single observer, if you're Freya, you don't know what to expect.
Professor Müller.
Yes.
Professor Müller, sorry for interrupting, but we are just about to get over with the allotted time of 45 minutes. So I
Yes,
request you
well,
to
now
kindly
it's 45,
summarize,
right?
conclude it as soon
Yes.
as possible.
Yes, I see. So my timer
Thank you.
shows me it's exactly 45 minutes now, so I'll go to the conclusions in 1 minute, okay? So this is an example of restriction A for one observer also, and even if you say, let's use Elgar's principle to tell Freya what you should believe, it's still the case for more than one observer. Good. Now, as a consequence of that, let me just skip this. But what I would say is that it's sort of unacceptable to have this case that there is no way for a single agent to guide their beliefs. So we should have a theory that tells at least single agents what they should expect to observe next, even if the situation is very exotic. Right? Now, if you say this is the fundamental thing to begin with, our observations are fundamental, the probability assignments are fundamental, then it's not so surprising that if you then say, what about now more than one observer? How do they combine? That they do not combine nicely into a classical picture of the world that has an underlying Kolmogorovian probability space. Good. So who's interested in that can have a look at my homepage, where I try to work out an approach that tries to address this. It's called algorithmic idealism. There are also 2 papers you might look at, which addresses this sort of restriction and gives a suggestion for how to answer it. And this brings me to the conclusions. So there were 2 parts. In the first part, I've shown you that quantum theory is just one of many probabilistic theory, and this can be used to derive quantum theory from simple principles without assuming the usual formalism. I've shown you one such reconstructions, but there are many, and also by other people, so you can pick one that you like more, perhaps. But this gives you a view that the quantum state is essentially a catalog of probabilities for what to see next, what to should believe to observe next. The second part, I've talked about the Wigner's friend scenario and what this view on the quantum state entails here and how it's generalized into a larger scape of problems in the foundations of physics. Formulated something like restriction A. Here's a link to the paper with Caroline, where you can look up the details of this construction. And I want to argue sort of that this motivates an approach where the first person is fundamental. Probabilities for which each agent should see in the future is the fundamental thing. And a kind of fragmentalist view of reality would perhaps emerge from this. With that, I would like to thank you for your attention. Thank you.
Thank you, Professor Müller. The first question is posed by Mr. Pandit from IISER, Kolkata. The question is, if the superposition principle is just a mathematical accident, what does that say about the reality of quantum states? Are they physical or just tools for a prediction?
Yeah, there's no clear-cut final answer from what I've told you. So these reconstructions don't exactly tell you how you must interpret quantum states. They sort of point you into a direction, perhaps of Neo-Copenhagen view, or that, quantum states are something like probabilities. but they do not even tell you how you should interpret probabilities, for example. There's a separate question, and they don't say in what sense the quantum state is real or not. So for me, the takeaway is that quantum states are just probabilities. Yeah, they essentially modal structure, similar as probability tables are. And when you ask, yeah, well, what is then there in the world, I would say, look, we have to adjust our view of what the world could be. We have this idea that there's this kind of external world out there, which has a kind of substance, it's kind of a strong oomph was really sitting there materially somehow, right? And then you think in addition to these probabilities, there must be something else somehow. I don't see this as the case. So I think it's probabilities and that's it. What you have is what you see and what you experience, right? And the rest is sort of modal structure that relates your experiences in some sense. Yeah. Where more questions come up, we have to say, how do different observers then agree and where we always see the same thing, but it's a longer story. And that's not something I say you must take away from this reconstruction business, but that's what I personally take away from it.
Sir, we have another question, another query actually. If quantum probabilities reflect an agent's personal expectations, does that mean the observer plays a real causal role in shaping outcomes? Or can this still fit it within the compatibilist view of agency in a law governed universe?
Right. So I'm not a cubist. So even though I admire cubism, who say that quantum states are states of belief of agents, I say all these reconstruction businesses, they are probability distributions, and then you can be agnostic about what these probabilities mean. I think they are sort of objective probabilities of what will probably happen, right? So not only what you believe, but what you should believe. Berghofer has written a nice paper on interpretation of quantum theory along these lines. And so it's a sort of objective probability of what will probably happen to the agent, right? And this doesn't depend on you necessarily wanting something or acting, right? But something will happen to you, perhaps depending on actions that you do. And it's not just your belief, it's what you should believe. Yeah, but it would be a very long discussion to go into the details of this. And this is just a sketch of how I
Uh,
tend to think about it.
I do understand if these contemplations go on, they could go on for hours. Thank you for keeping the answers crisp and short. I'd like to take one more questions amongst the ones raised by the participants. That is, how can I meaningfully speak about laws of nature, given that quantum mechanics only guides my expectations about future observations?
Well, so as I said, I'm not claiming that the quantum states are your expectations of future observations. It is the expectations of future observations that you should hold, right? So it's not just your beliefs. It's more sort of probabilistic structure, modal structure of what will actually happen, believe it or not. So you can have beliefs that are completely separate from the actual probabilities that would be determined by quantum theory, for example, in that view that I'm defending here, right? And so there's a much more stricter notion of objectivity built into this view than if you're just like say everything are beliefs and you're a subjective Bayesian. Now you may still ask, well, even if I have that, I feel kind of uncomfortable. Isn't there something more I should say about the reality of things out there and so on? But then I would say that the message of modern physics is just that whatever is out there and whatever reality is tends just not to follow our human intuitions very much. So yeah, you can think of what space-time, for example. Yeah, it's just not the thing we thought it is, like this stage, like that's rigidly sitting there and everything unfolds in it. No, it can also be dynamic, right? And you can transform coordinates as you want. It's like unphysical, it's just gauge. So all that's real is sort of in general relativity, the kind of point collisions and so on. So it's already counterintuitive. And I think physics makes like whatever physics developments will happen will probably make it even less intuitive. Right? So for me, there is no problem in saying it's essentially modal or probabilistic structure that's real, as long as one can tell one can work out rigorously that this will reproduce what we see, so that there isn't a miracle remaining. If your theory where it's a miracle that your friend in the laboratory sees the same outcome as you, then it's not a good theory. But if you say maybe there is no outcome that's kind of absolute in the usual sense, but I can still understand why when I go with my friend in the laboratory, we see the same outcome, then I say it's a good theory. And I don't even miss this kind of ontological, intuitive feature that there must be this absoluteness of underlying things and stuff necessarily.
Professor Müller, we have amongst us Professor Tejinder Singh, ex-professor from Tata Institute of Fundamental Research and visiting professor at Inter-University Center for Astronomy and Astrophysics. He has a query. I would like to request Professor Singh and Professor Müller, both of them, to keep the discussion to the minimum as much as possible. So over to you.
Thank you for a very nice talk. I have a comment and a related question for the first part of your talk about box world theories. So there are a couple of examples in the literature of box world theories. One is Stephen Adler's theory of trace dynamics, which generalizes quantum theory in an attempt to derive collapse models from more general underlying principles. So trace dynamics under certain conditions admits violation of the Cyrilson bound. And second is an attempt to explain quantum non-locality by generalizing special relativity to higher dimensional space-time with additional dimensions or time. Like here again, one sees violation of the Cyrilson bound. What is not clear is exactly what kind of experiments might one do to rule out box world theory. So do you have some ideas? No. Why is it that in Bell correlation violations, we never see anything going beyond Cyrilson? Is it that we are not looking for in the right place, maybe high energy experiments? Or you are convinced that Boxwell theories are not there in nature?
It's a very good question. So I have a lot of sympathy for the idea to look into new regimes, perhaps in high energy physics, and to ask whether there could be more general correlations. Example correlations that could be, say, more physical even than the box world ones, but still larger than quantum is what's called, say, almost quantum correlations. They're slightly larger, still have extremely nice properties, and there are some hand-waving arguments why one could expect some of them in quantum gravity or so. So that's what I'm familiar with. I'm unfortunately not so familiar with trace dynamics, but thanks for telling me about this. I'll try to look it up. Maybe you can even send me a reference about this. However, so one thing I would like to ask back is that often when you get certain new phenomena that introduce a sort of non-locality into the physical setup, and not only do you then say violate the Cyrilson bound, but you typically also get signaling. So is this the case in the proposals that you mentioned?
No, no. The good thing about both trace dynamics and the theory with higher time dimensions, both are local. There, no signaling is imposed as a requirement. In fact, it's very interesting what's happened. I'll talk about this tomorrow. So what we are considering is, suppose space-time is not 3 plus 1, 3 space and 1 time, but 3 plus 3, 3 space and 3 times. And for some reasons, the additional time dimensions are very tiny, they are compact. But when you allow for that, events which are causal or causally connected and local in the higher dimensional space-time will start to look space-like separated if you did not know that there were additional time dimensions. So in fact, it's a good way to restore locality and completely obey no signaling. So no signaling and causality, but non-locality only as an apparent or an illusion kind of situations, because my detectors are in 4D, but quantum theory is playing out in 6D. If I only went and looked for those additional time-like dimensions, I realized, oh, everything is local. It's not deterministic, but it's local.
That sounds very interesting. So maybe you can send me a reference. I would love.
Okay, I'll do that. Thank you. Thank you.
Great. Thank you. Thank you for the comment.
Thank you, Professor Singh. Thank you, Professor Müller.